So, we continue with our discussion on physical synthesis. In our last lecture, if you recall, we talked about two techniques, gate sizing and buffering, introducing buffer in interconnection lines. So, we continue with our discussion. So, we look at the third broad approach in this lecture, netlist restructuring. So, as the name implies, we are trying to modify a circuit netlist in some way, and there are many ways in which you can do that. Now here, as I said, that we are modifying the netlist in some way. Our objective is to improve the timing, but quite naturally we do not want that by this modification the circuit functionality should change. That should not be modified. Okay, the circuit functionality should not be modified, but we can use some additional hardware, like some additional gates may be required, some additional connections may need to be added. So, we shall see a number of various techniques here. This list is not exhaustive. Some of the very common netlist modification techniques are as follows: cloning, which as the name implies, we do some kind of cloning or duplication. Here we duplicate gates. We can redesign fan in or fan out tree networks. We can swap commutative pins of some of the gates. We can decompose some gates using some simple Boolean algebra rules, and here again using Boolean algebra rules we can restructure some circuits. So, we can implement them in different ways, so that the timing characteristics are improved. Let us see one by one. Cloning. Cloning, as the name implies, that we sometimes may need to duplicate a gate. So, what we are actually talking about, let me first intuitively tell you, then I shall talk further. Let us say we have a gate. This gate output may be going to more than one place. So, by cloning, what we are doing, let us say the inputs are A and B. So, we are saying that we are replicating this gate. Same gate we are replicating twice. So, here it may be going to many of the fan out points, but here we are sending this output to a subset and this output to the other subset. So, maybe we are splitting the outputs across these. So, why we may need this cloning? There can be two broad reasons you can think of. First is that in this case there can be a large number of fan out connections, which means you may be having a large value of load capacitance, which means this gate will be driving those load capacitance, charging and discharging will become slow. So, the overall gate delay will be large, but here we are distributing this CL among two parts. Well, if they are equal, let us say I divide it up into CL by 2 and CL by 2. So, my delay will become approximately half, right. So, here my consideration is only with respect to the charging and discharging times. If I can reduce the load capacitance, my charging discharging time can also reduce. So, there can be another reason, like say let us look at my total layout. Let us say my this NAND gate was here and the output was going to so many different places. Let us say, so some of the outputs were going here, these were the 3 points where it was going, but the other outputs were going somewhere which are quite far apart. Let us say far apart means this each of these long lines will contribute to a long interconnection delay. So, intuitively these gates can be inserted either to handle this or to handle this long interconnection lines. maybe instead of driving directly this long line, you replicate it, and another copy you use which will be used to drive these, and this gate you can locate in a suitable position, not here, maybe you can place it here or here. Okay, fine. So let us come back. So just as I have explained, gate duplication or cloning can reduce delay for the following two situations. First, when the gate fan out is large, so we can split the total fan out between these two gates, so the fan out capacitance will become less effectively. Secondly, if in the other case we just explained that if the gate's output goes to two different regions or two different directions, so that you cannot find out a good placement of this gate, where to place it, because the outputs are going in two different corners of the chip. So even if you place in the middle, still the length of the wires may be longer. So better to use two copies of the gates, one you place closer to that, other you place closer to that, okay, and you just clone like that. So the effect of cloning, just now we have seen, is to split the driven capacitance between two equivalent gates. That means the output capacitance CL was getting divided into CL by 2 and by CL by 2, but at the cost of increasing the fan out of upstream gates. What does this mean? Let us see here again. Initially this input A was coming to the single input of NAND gate, but now this input A must come to two different places. So I am effectively increasing the fan out of the line A and also B. So now A is having a fan out. Okay, this is what we refer to as the upstream gates. Okay, so these inputs which are coming after cloning, they have to be driven, both of this A and both of this B has to be driven. Okay, okay. So this is what we refer to as increasing the fan out of upstream gates. And the second one we mentioned, if the output is going in two different directions, so we can replicate gate and place the clones closer to the downstream logic. Downstream logic means the circuits which are towards the fan out side, so we can place closer to that. Okay, so let us take an example. We will use that same delay, capacitance delay model that shown earlier. So we take an example like this, where I have a NAND gate which is driving 5 fan out connections with a total load capacitance of 5. So this is B, the gate size B we have taken. So let us look at it once more. For gate size B, for 5 femtofarad capacitance, the delay was 45 picoseconds. So for this case the delay is 45 picoseconds. Now cloning we are doing like this. This we are splitting in two. Let us say one of them is VA, other is VB. It is not necessarily true that all these gates have to be of the same size. So it may be so that we may have to be, say here for example, here this VA is driving 2 loads, VB is driving 3 loads. Because here the load is higher, we are using a larger gate here, and because the load is less here, we are using a smaller gate here. Okay. So VA with capacitance 2 and VB with capacitance 3. Let us see. VA with load 2, it is 30, and VB with capacitance 3 is 33. Okay. So this will be 30 and this will be 33. So instead of 45, now the delay is coming to 30 here and 33 here. We have been able to reduce the delay, right? But as I said, the fan outs of A and B are increasing. Now this A will be having one additional fan out, B will also be having an additional fan out. And when the downstream capacitance is large, buffering can be better than cloning. You see here the reason is that buffer do not increase the fan out capacitance of upstream gates. Like here what I am saying is, let us say I have a scenario where I am driving some load. Suppose this load is large, I am driving a large capacitor. What I am saying is that here maybe buffering is a better option instead of cloning. So, cloning, what you are saying that cloning, by cloning we are sharing the load, okay. Some part of the load we are sharing here, some part of the load we are sharing here, dividing up, okay. So, we are saying that in use of buffer can be better in cases where you are driving somewhere where the load capacitance is very large, because the advantage of buffering is that, say at the input side you are not increasing the fan out of the load capacitance, this capacitance remains the minimum capacitance. But here if you are using, like here, suppose if this is C, then the effective capacitance here will become twice C, because you are driving 2 gates now, right. This is what I am just referring to here, because buffers do not increase the fan out capacitance of upstream gates. But of course, placement driven cloning is a very powerful concept, as we said that if there are some fan out targets which are located in somewhere else of the chip, some other part of the chip, then a clone of the driving gate can be placed closer to that. This will consist of the so called placement driven cloning. You are doing cloning not just by looking at the loads and other things, also you are looking at where they are going. If you see that there is a cluster here, you place a place a copy of the clone near to that cluster. If there are some other points going there, you place another copy of the clone near to that cluster, okay, like that you do. Okay. So, let us take an example here. Let us say here there was a gate which was driving 5 signals D, E, F, G, H. Well, let us say D, E, F are close together, close to V, but G and H are a little farther away. So, what we are saying is that you clone a gate and this new copy V dash you place it closer to G H, you do not keep it adjacent to V, keep it a little farther, maybe these wires will become longer, but this delay will become much less. Fine. Now, the other techniques, redesigning of the fan in tree. Redesigning of the fan in tree means whenever there is a fan in connection, just in gate, let us take an example like this. Suppose means we have a gate netlist like this. Here the type of gate is not important, just there are 3 gates in 2 levels, A, B, C, D are the inputs, and the actual arrival time of these inputs are shown 4, 3, 1, 0, which means the first input is arriving late, the last input is arriving earliest. Okay. Now, if I implement this gate like this, this 1 denote the delay of the gates. If we implement this function like this, then the output will be available only after 6 units of time, because one of the input A is coming only at 4, then 1 and 1, 6. But suppose I do it like this. Now, apparently for a logic designer will say that, well, this is a bad design. Here I have 2 levels, that means the delay was 2, here is a 3 level, so the delay should be 3, but okay, delay may be 3 in the static cases, but if you look at the arrival times, this realization is better with respect to timing. Why? Because the slowest input A is encountering only one gate delay. So, now the output will get ready by 5, because 1 and 1, this output will be ready by 2, 3 and 2, this output will be ready by 4. So, this output will be ready by 5. So, here the output was coming at time 6, but after this restructuring, your actual arrival time of the output is becoming 5. Okay. So, this is the advantage. So, fan-in restructuring means this: whenever there are a number of lines coming at the input of the gates, but using simple Boolean rules, you can redesign the network such that the slowest signal lines you try to put in a place which will get the fastest route to the output, like here we have done A. Okay. Fine. Similarly, we can do for the output side, like not only the input lines, but also the output load capacitance we can balance across the different segments. Let us take an example. First, we shall come back to the slide again. Let us see the example first. Let us suppose we have a circuit like this, where there was a gate here with a delay of 1. There are 2 buffers y1 and y2. Let us say this path I call it as path 1, this path I call it as path 2. This buffer was driving these 2 lines, and this buffer was driving this line, let us say. But here what I do is that, let us say we see these lines are ultimately coming from the same source, the same fan out I have broken up using buffer into this 1, 2 and 3. Now, suppose this one of these lines I can move it to here from here like this. So, if I do it, then possibly I do not need this buffer anymore. Okay, here I have not shown this, may be going to other places also. So, one of the paths, one of the buffers might get eliminated. Now, maybe it was the case that path 1 was the shorter path, we are trying to make it faster. So, this may be one method to do it. So, let us go back to the slide. So, in the example we just saw, this y1 was required because the load capacitance of path 1 was large. Okay. Load capacitance of this path 1 was large, you see it was driving 2 fellows, 2 inputs, that is why we needed a buffer here. So, by redesigning the fan out tree, what we did, we reduced the load capacitance of path 1, and so the buffer y1 was avoided. So, this we shifted to here. This buffer was already there, so it was already driving, so it is no problem, but this buffer we can avoid, right. But this increased delay of path 2 we can accept, suppose it was not on the critical path. Okay. So, if you do this kind of transformation, naturally the load on the second buffer will increase. So, the delay on path 2 will increase, but maybe this path 2 was having sufficient positive slack. So, this was not critical at all. So, even because of this additional increase in the delay, this still remains with a positive slack. So, this can be acceptable. Okay. Fine. Swapping commutative pin means there are many gates where if you swap some of the pins, they remain functionally equivalent. Let us take some examples. Let us take a 3 input AND gate ABC. You see this output is A, B and C. Now, if you swap the gates like CAB, it is same, or CBA, they are all same, because this AND function is commutative, AB is equal to BA. So, you can use this that rule of you can use the rule of commutativeness to prove this easily. Okay. Similarly, the basic gates are all commutative in nature, NAND, OR, NOR, just even exclusive OR. They are all commutative in nature. You can swap your inputs in any way you want, the output function will not change, they will remain functionally the same. But suppose I have some other functional block, let us say a multiplexer. I have a multiplexer, I have A, B and this select line S here, and this is the output. Now, suppose I say that I swap my inputs, I make this B, I make this A, this function will not be equivalent to this. Okay. This is not equivalent, because if S equal to 0, in this case A was selected, but now here B will get selected. Okay. So, there are certain functional blocks for which you cannot do this swapping of the pins, and the pins which can be swapped, they are called commutative pins. For all the basic gates, the pins are all commutative and you can easily swap all of them, right. So, this method says that you can swap commutative pins. Okay. Now, another thing you observe, at the level of gates, this looks very fine, that if you swap there is no change, but if you look at a transistor level circuit, let us say I am just showing you one simple example, a 3 input NAND. So, a transistor level circuit will consist of, in the pull up there will be 3 p type transistors, let us say A, B, C, and in the pull down there will be 3 parallel transistors N type. Now, this output may be driving some load capacitance, okay, CL. This is VDD. Now, what I am saying is that, well, although we are saying that this gate is commutative with respect to the inputs A, B and C, let us say the output is F, this is F, but you see when this A is switching, right, suppose B and C were already 0 and 0 and A was 0, A is becoming, A was 1, it is becoming 0. So, B 0 and 0 means this was conducting, this was conducting, A was 1 means this was off, now this is conducting. Now, when A is conducting, so this will be the path. Now, the other case is that when I talk about C, this A, B were already conducting, now I have to consider the delay between this point and this point only. So, the net delay or the signal propagation delay need not be all from VDD to here. For some cases I may need to take the whole path, some cases shorter paths. So, the delay across the pins can also be a little different, okay, for a gate. This is what we are trying to say. So, here what I am saying is that in the actual transistor level netlist, the commutative pins which are so functionally can have different delays. So, rule of the thumb is that if a signal is coming later, you assign it to an input pin which is faster, but if a signal is coming earlier, we can assign it to a pin which is slower, just the rule of thumb. So, just a simple example is shown here. These indicate the delays of the inputs, like these are 2 input gate, both delays are 1 and 1, here it is 1 and 2, and these are the arrival times. So, for this realization, the output arrival time will be 2 plus 2 plus 1, 5, but if I make a commutation in the input, I bring C here, B and A here, then 0 1 0 is the earliest. So, by 2 this will be ready, so by 3 this will be ready. So, from 5 we have reduced the delay to 3. Okay. So, this is also one kind of a technique in which you can adjust the inputs by commuting them, so as to improve the delay. And the last one is gate decomposition, means there are some rules of Boolean algebra, so using which you can decompose gates into smaller gates. Well, the reason is twofold. One is, of course, if you divide into smaller gates, maybe the overall delay will become less, and also for a larger gate your MOS level, transistor level network can be very complex. There will be more capacitive effects involved, delay will be larger, but if you can break it up into smaller gates, that can be advantageous in some cases. Okay. So, in this slide we are showing a simple example. Suppose there was a 2-level AND OR realization. Now, you know that any 2-level AND OR is equivalent to a 2-level NAND. So, this is equivalent to this. So, I can have a realization like this. Here we need 3 2-input NAND gates and 1 3-input NAND gates. But this 3-input NAND gate you can possibly break it up into a 2-input AND followed by a 2-input NAND. So, here we have an alternate realization where all the gates have 2 inputs only. So, this kind of a transformation may also have an impact on the delay, because in this case the delay of a 2-input gate and a delay of a 3-input gate will not be the same, they will be different. Okay. But here we are trying to make them uniform. And Boolean restructuring is a technique where you can use the rules of switching algebra or Boolean algebra to find out some common sub expressions essentially. And there is an example which is shown in the next slide, which uses the distributive law of Boolean algebra, which says that A or BC is the same as A or B and A or C. Right. So, this kind of a distributive law you can use to improve timing, and in the example we are taking two functions, one is x equal to A or BC, other is y equal to AB or C. Right. We shall come back to this. Let us see the functions first. So, this x is the function, let us recall A or BC. Okay. Now, using distributive law you can write it as A or B into A or C. Okay. Similarly, y was A, B or C. So, using distributive law you can write A or C, B or C. So, just exactly like this we have implemented this A or B, this implements A or C, this implements B or C. So, by just ending the required 2 OR outputs you get x and y. Now, if we assume that the input arrival times of the inputs are 4, 1 and 2, A is coming at 4, B at 1, C at 2, 4, 1, 2. So, the delay will be 4 plus 1 plus 1, that is maximum, both the cases 6 and 6. But now, suppose we are not using this way, we are using straight implementation like this, A or B C, A B or C. That means, we are using AND in the first level or in the second level. So, you see, since A is coming out straight, so here the delay will be 5, but Y is still 6 because A is coming at 4, then you need to get delays. So, at least one of them we are able to speed up, right. So, with this we have seen a number of techniques using which you can restructure a netlist, so that some, you can say, characteristics with respect to timing can be improved, because we need a lot of this kind of corrective actions to be taken after we carry out static timing analysis. We find out that there are a lot of timing requirements which are not being met. We may have to make a number of changes and transformations the circuit, netlist, placement. So, we have talked about some of these techniques which are quite commonly used. So, in our next lecture we shall be continuing with this. We shall be looking at the overall performance driven flow, that what we have learned so far, that what it looks like in an integrated sense. Thank you.